And now for the last thing, why is that pesky character of 2 present in that equation of motion? What's the big deal about that? Why not 4? Why not 8? Why not 2.735? Right? These are all questions that you should ask. If you see something that is completely arbitrary, ad hoc, why the hell is it there? So look at this. One by f of t, x of 0 is x naught. What's the characteristic equation of the system? Can somebody help me write it out? Okay, go for it.
1 plus 2 zeta omega n plus omega n squared.
There has to be an s somewhere. You're close. Yeah, you're close. What's the characteristic equation? You're close, very close. If I say a double derivative, what should I see in the Laplace transform? I should see I need to see an x square. Laplace transform of an x double dot gives me an s square times an x of s. Right? So the first term is going to give me an s square. From the second terms, discounting all the initial conditions because they're not an inherent property, we're looking at the characteristic equation 2 zeta omega n s omega n square. Okay? This is the characteristic equation. I'll set it equal to 0 to find the roots. This is the characteristic equation of second order. Characteristic equation of first order systems, s plus 1 by tau is 0. Please remember these things. These are all fundamental things, and I know you have a lot of things to remember, and memory is a thief of time, right? So you lose memory as you go on, but remember certain things. I calculate the roots of this guy. So s, obviously it's a quadratic, so it is hopefully going to have 2 roots. One of them could be 0, which would be great. Unfortunately not. 2 times zeta. I'm sorry. Okay. 2 times. I'm solving for s, so 2 times zeta omega n. Okay. Then I'm going to have plus or minus. So it's minus b. B is this particular term, plus or minus b square, which is 4 zeta square omega n square, minus 4 times the coefficient containing s square is 1, so 4 times omega n square, because that's the term. All of this divided by 2. Right? This is how we find the roots of the quadratic equation. Am I right? You see why the 2 is there? Because I can take a factor of 2 out of all of these things. Okay, so I can just get rid of all of this 2 stuff, and I have the roots minus zeta omega n plus or minus. I can take omega n as a common factor as well, so I'm going to do that. So that's going to be plus or minus omega n squared. Square root of that is omega n times theta square minus 1. These are the roots. And you immediately recognize there are going to be 3 cases for these roots. If zeta is a number greater than 1, you're going to get real and distinct roots, or real and repeated roots in some sense. Okay? If zeta is a character equal to 1, then that thing completely vanishes. You're going to get real and repeated roots. If zeta is less than 1, you're going to get complex conjugate roots because the character inside the square root becomes imaginary. Okay? So I'm going to write these 3 cases down last minute. Zeta less than 1, real and distinct. Zeta equal to 1, real, repeated. And zeta less than 1, complex conjugates. For real and distinct, I'm going to get behavior that can show some oscillations. For real and repeated and complex conjugates, perhaps there is a situation of oscillation as well, or just something that damps down. Okay, so we'll look at all these situations in the next week. And so real and this thing should be exponential decay. Complex conjugates will be oscillating. Thank you.
Those are both the same comparison side.
Same.